Well, hello everyone. In this video, I wanted to explain what is the procedure that we can use in order to compute the Laplace transform of any function, but also how we can compute the inverse Laplace transform, and also how we can use the Laplace transform to solve differential equations. Okay? So remember that the definition of the Laplace transform, okay, is equal to the integral that goes from 0 to infinity of f of t times e elevated to the minus s times t dt. No, this is the definition of the Laplace transform. And basically what we are doing is to map the function from the time domain to the s domain, okay? And if we compute the inverse Laplace transform, we are basically mapping the function from the s domain to the time domain, okay? And well, remember that S is basically a frequency domain representation. Okay? So in order to understand how we can use this tool in order to solve differential equations, and also we can generate a mathematical model that allows us to understand the dynamics of a system, we need to use this tool. So for example, the first thing that we can do is to compute the Laplace transform of a function. And the good thing is that thanks to the properties of the Laplace transform, we can use tables to compute this transformation. So for example, here we have a function that is e elevated to the 4 times t plus 5. Okay, this is the function, and we need to compute the Laplace transform of this function. So we know that the function f of s is equal to the Laplace transform, okay, of e elevated to the 4 times t, okay, plus the Laplace transform of 5, okay? We can apply the Laplace transform to each term individually, okay? And also, in order to avoid confusion, I will write the s in cursive manner, okay? This is the s in cursive form. So I would write this as follows. F of s is equal to the Laplace transform of e elevated to the 4t plus the Laplace transform of 5. Okay? So we can first compute the Laplace transform of this term. So the Laplace transform of this term is e elevated to the 4 times t. Okay? And also we know that thanks to the tables of the Laplace transform, we know that there is a relationship to compute the Laplace transform of an exponential. And the relationship as follows. We have a function e elevated to the minus a times t. And the Laplace transform of this is 1 over s plus a. Okay? I will write this s in cursive form. Okay? And now, if we compare these two functions, they look very similar. In fact, if we compare these two, we can notice that minus a should be equal to 4. So we can say that a should be equal to minus 4. So if we apply this relationship in order to compute the Laplace transform, we can see that the Laplace transform should be equal to 1 over s. And in this case, we know that a, according to our function, should be equal to minus 4. Okay, so this is the result, okay, of this term. And we can do a very similar thing to the following term. The Laplace transform of 5 is equal to, well, we can factor the 5, okay? We can factor the number 5 in this way. And I can factor from out of the transformation the number 5, and we have here a 1, okay? Now, we also know what is the Laplace transform of number 1. Now, when you have a constant or a number equal to 1, you can compute this as follows. The Laplace transform of this is 1 over s. Okay? So we can say that the Laplace transform is basically 5 times 1 over s. So the Laplace transform is equal to 5 over S. Okay? So now we know all the results. We know we have the Laplace transform of this term, that is this one, and also the Laplace transform of this term, that is this one. So the Laplace transform should be equal to 1 over S minus 4 plus 5 over S. No, this is the value of the Laplace transform. Okay, so this is one of the examples that we can make. And I will make another example, no, in order to show you how you can compute the Laplace transform. For example, we have now the following function. We have f of t is equal to the cosine of 2 times t plus 7 times the sine of 2 times t. Okay? So we can compute the Laplace transform as follows. We have the function f of s is equal to the Laplace transform of the cosine of 2 times t plus, I will factor the 7 out of the transformation. Okay, we can do that for constant values. So I will compute the Laplace transform of the sine of 2 times t. Okay, now we also have tables to compute the cosine and the sine wave. So the Laplace transform of a cosine is equal to s divided by s squared plus omega squared. Okay, this is the Laplace transform of a cosine function. So if we compare these two functions, you can see that the value of omega, according to the cosine function, is equal to 2. Okay, so we can compute the Laplace transform of the cosine of 2 times t as s divided by s squared plus omega squared. But in this case, we know that omega is equal to 2. So we can say that the Laplace transform is equal to s divided by s squared plus 4. Okay, this is the value of the Laplace transform of this function because we have a cosine. And we can do a very similar thing for the sine wave. Okay, we know we have a table that relates the Laplace transform of the sine wave. Okay, and this is equal to omega divided by s squared plus omega squared. Okay, so based on this, what we can do is to say, okay, we know the value of omega, this is equal to 2. So we can compute the Laplace transform as follows. The Laplace transform of this term is 7 times the sine of 2 times t, that is equal to 7, okay, times omega, but in this case, we know the value of omega. Omega is equal to 2, okay, based on this relationship. And this is divided by s squared plus omega squared, but omega squared is 2, so this is equal to 4, okay? So we can say that the Laplace transform is equal to 14 divided by s squared plus 4. So the Laplace transform is as follows. We have s divided by s squared plus 4 plus 14 divided by s squared plus 4. And this is the result. Okay. So this is the Laplace transform of this function. And we can make another example. Let's say that we have the following expression. We have f of t is equal to e elevated to the minus 2 times t times the cosine of 3 times t plus 5 times e elevated to the minus 2 times t times the sine of 3 times t. Okay? Now we also have relationships that, or tables that relates the multiplication between an exponential and a cosine function. So for example, for a cosine function, we know that the Laplace transform is follows. No, and a cosine multiplied by an exponential, the Laplace transform can be defined as e elevated to the minus a times t times the cosine of omega times t. And the Laplace transform of this is s plus a divided by s plus a squared plus omega squared. Okay, so omega is equal to 3. Okay, if you compare these two, you can see that omega is equal to 3. And also, we can see that minus a should be equal to minus 2. So minus a should be equal to minus 2. And we can now compute the Laplace transform of the first term. So the Laplace transform of this term is e elevated to the minus 2 times t times the cosine of 3 times t. Okay? And this is equal to, well, based on the relationship that we have here, we can see that the Laplace transform is equal to s plus a, but in this case, a should be equal, well, based on this relationship, we can conclude that a is equal to 2, okay? No? A is equal to 2, and, well, this is divided by s plus a, in this case is 2, square, plus omega squared, that is 3 elevated to the second power, okay? And to, this is equal to s plus 2 divided by s plus 2 squared plus 9, okay? So this is the way in which you can compute the Laplace transform of this type of function. But also we need to compute the Laplace transform of the other term. So we know that the Laplace transform of 5 times e elevated to the minus 2 times t times the sine of 3 times t, okay, is equal to, well, we can factor the 5, okay, from the Laplace transform. We can also factor the constants, okay, and we have here e elevated to the minus 2 times t times the sine of 3 times t. And this is equal to, well, we know the Laplace transform of a sine wave multiplied by an exponential. And this is equal, well, the Laplace transform of an exponential multiplied by a sine wave, okay, is equal to omega divided by s plus 2 squared plus omega squared. And if you compare this, omega is equal to 3, and a should be equal to 2. Okay, so again, we can substitute these values into this relationship to compute the Laplace transform. So we have here 3 plus, well, here I was making a mistake. Remember that this is a. So we know s plus a, that in this case is 2, square, plus omega squared, that in this case is 3. So the result is 9. Okay, so this is the result. Okay, I will erase this, and we have here a 2. Okay, so this is the Laplace transform of this term. So we can say that the Laplace transform of this function is equal to this, the first term, that is s plus 2 divided by s plus 2 squared plus 9 plus 3 divided by s plus 2 squared plus 9. Okay, so this is the result that we obtain. And what else? Well, this is one example, no, in how you can use the Laplace transform, or how we can compute the Laplace transform. But also, I wanted to show you how you can also compute other types of transformations. For example, how can we compute the inverse Laplace transform? So just let me a moment. I will show you that in a minute. Well, Take for example, now we want to compute the inverse Laplace transform. And that means that we have a function defined in the S domain, and we need to transform this function in the time domain. Okay? So take, for example, the following exercise or the following function. Imagine that um, we have the following the function that is um, f of s is equal to 2 divided by 3 over times s elevated to the 4th power, no? This is the function. So the idea is that um, we need to find a table in the Laplace transform tables that is very related to this function or that is close to this function, okay? So what I recommend to do is that first, what we can always do is to factor the constants, okay? So here we have a constant at the top that is 2, and also we have a 3 at the bottom, times 1 over s squared, okay? And if you look very closely to this term, you can see that it looks very similar to the Laplace transform, okay, of a polynomial, okay? Or a function elevated to the n power. And we know that the Laplace transform of that is n factorial divided by s elevated to the n plus 1. Okay? So here we have that n plus 1 is equal to 4. Okay, we compare these two. The problem is that we don't have the n factorial in this expression. Okay? But we can solve this equation for n. Now we have n, it should be equal to 3. So we are missing in this expression the n factorial at the denominator. So what you need to do, or what we can do, is to multiply the numerator and the denominator of this function by the factorial, that in this case is 3. So this is equal to 2 divided by 3 times 3 factorial, okay, divided by 3 factorial, times 1 over s elevated to the 4th power. And this is equal to 2 divided by 3 times 3 factorial times 3 factorial divided by s. Well, I will express this power as follows. Remember that n is equal to 3 plus 1. Okay, so now this expression looks very similar to the expression that we have in this side. So we can apply directly the Laplace transform to this term, no? The inverse Laplace transform. So we can say that the inverse Laplace transform of f of s should be equal to 2 times 3 times 3 factorial times the inverse Laplace transform of 3 factorial divided by s elevated to 3 plus 1. Okay? And we can compute directly this inverse Laplace transform as 2 divided by 3 times 3 factorial, and this is multiplied by t elevated to their power. Okay? And this is equal to, well, if we simplify this further, you will notice that we have the following result, that is 1 over 9 times t elevated to the third power. Okay? So we have computed inverse Laplace transform, so we can say that f of t is equal to 1 over 9 times t elevated to the third power. And this is the final result. Okay, this is the way in which you can compute it. Okay, let's make another example. Now imagine that we have the following function. f of s is equal to 1 over 3 minus 4 times s plus um, plus 3 minus 2 times s divided by s squared plus 49. Okay, so one of the things that we always need to do is to always expand the function to the best we can. So one way to expand this function is as follows. First, what we can do, well, we can write the first term as it is. We have 3 minus 4 times s. Plus, but we can expand this as follows. This second term as 3 over s squared plus 49 minus 2 times s divided by s squared plus 49. Okay. And now with this information, what else we can do? Well, we need to apply the inverse Laplace transform to each term. So I will apply the inverse Laplace transform to this term first. So we can say that the inverse Laplace transform of 1 over 3 minus 4 times s is equal to, well, we can factor the minus 4. Okay, so we will have, well, we have here the inverse Laplace transform of 1 over 4. I am factoring this minus 4 times 1 over s minus 3 over 4. Okay, and now we also have, we need to look at the Laplace transform tables to see which table is useful for us. So there is this is very, well, this looks very similar to the Laplace transform of an exponential. No? Remember that the Laplace transform of an exponential is e elevated to the minus a times t. The Laplace transform of this is s plus a. Okay. And what else we can do? So the idea is that we have the following. We can compare the two functions, this one and this one. And here we can conclude that a should be equal to minus 3 over 4. Okay? So we can compute the Laplace transform of this first as follows. Well, we can get rid of this constant. Okay? We can consider that out of the inverse Laplace transform. And we can obtain the following. We have 1 over 4 minus 1 over 4 times the inverse Laplace transform of this function. But we know that the inverse Laplace transform should be equal to e elevated to the minus a. But in this case, minus a, well, a is equal to minus 3 over 4 times t. And this is equal to minus 1 over 4 times e elevated to the 3 over 4 times t. Okay? Well, this is only for the first term, but also we have the following term, this one. Okay? So to compute that, we can also do the following. We know that the inverse Laplace transform is 3 divided by s squared plus 49. Okay. And my recommendation always is that you factor always the constants. So we can factor the constant at the denominator, that is 3 times the inverse Laplace transform of 1 over s squared plus 49. Now we need to again look at the tables. So if we go to the tables, you will notice that we have the following relationship. No, this looks very similar to the Laplace transform of a sine wave. So the sine of omega times t, the Laplace transform of this is omega divided by s squared plus omega squared. The problem here is that, well, we can conclude based on this or on this comparison that omega squared should be equal to 49. So omega should be equal to 7. The problem is that in the denominator, we don't have omega. So what we need to do is to multiply the numerator and denominator by 7, or by omega in this case. So we can say that 3 over 7 times the inverse Laplace transform of 7 over omega squared plus 49. Okay, we need to compute the inverse Laplace transform. But based on this expression that we obtain by multiplying the numerator and denominator by 7, we can now apply directly the inverse Laplace transform, that is this sine wave. So this is equal to 3 over 7 times the sine of omega, that in this case is 7 times t. Okay, so this is the Laplace transform of this term, but we are missing the last one, no? That is the inverse Laplace transform of minus 2 times s divided by s squared plus 49. And this is equal to minus 2 times the inverse Laplace transform of s divided by s squared plus 49. Okay? Now, this looks very similar to the inverse Laplace transform of a cosine. Okay? So the Laplace transform of a cosine is s divided by s squared plus omega squared. And if we compare this omega squared with this 49, we can say that omega should be equal to 7. So we can compute directly the inverse Laplace transform as minus 2 times the cosine of 7 times t. Okay? And well, this is the, the, the result of this part. So now we can add all the terms. We have that the Laplace transform of the function f, of the inverse Laplace transform of this function f of s is minus 1 over 4 times e elevated to the 3 over 4 times t plus 3 divided by 7 times the sine of 7 times t minus 2 times the cosine of 7 times t. And well, this is the result of each term. Okay. So now we have this result. Okay, there is no problem with that. Now we have seen how we can compute both the Laplace transform and the inverse Laplace transform. So one last thing that I want to introduce is how we can compute differential equations. No, now we know how we can compute the Laplace transform and the inverse Laplace transform. Okay. So in order to compute differential equations, we can use the following relationships. So, for example, if you have a first derivative, okay, the Laplace transform of a first derivative of any function is equal to s, I will write s in cursive manner, to maintain consistency, s times the function x in the s domain, okay, in the S domain minus x at the initial condition of and the initial condition of the function at t equals 0. Okay, here we need only to multiply. If we have a first order derivative, you only need to take s and you multiply the function s by x of s minus the value of the initial condition at time t equals 0. Okay, so we need to use this expression. And if you have a second order derivative, the Laplace transform is s squared times x of s minus s times the initial condition of the function minus the initial condition of the first order derivative. Okay? So we can use these expressions in order to compute the Laplace transform of derivatives. So based on these definitions, what we can do is now see how we can compute these Laplace transforms, okay? So let's consider the following case, okay? We have j prime plus y is equal to 3 times e elevated to the 2 times t. And we have the following initial condition, that is y times equals 0 is equal to 4. No, this is the initial condition at time t equals 0, no, at the beginning of the analysis. So the approach is that we need to apply the Laplace transform to all of the differential equation. So we apply the Laplace transform or to y prime, okay, plus the Laplace transform of y. And this is equal to 3 times the Laplace transform of e elevated to the 2 times t. Okay. Now, here we have a first order derivative. Okay. So the Laplace transform of this, as we defined previously, should be equal to s times y of s minus the initial condition. Okay, that is this one. Plus the Laplace transform of y. And this is equal to y of s. Okay, that is equal to 3 times the Laplace transform of an exponential. But we know, thanks to the tables, that the Laplace transform of this type of exponential is 1 over s minus 2. Okay? Now, well, I can substitute the value of the initial condition. We have s times y of s minus 4 plus y of s. And this is equal to 3 times 1 over s minus 2. Okay? Now, we need to solve the differential equation for y. Okay, that is the variable that we are studying. Okay, is the variable that is changing with time. So what we can do is say, okay, we have 3 times 1 over s minus 2. I can move the minus 4 to the other side. We have 4. And we have here, we can factor, we have these two terms. And I can express this term and this term as follows. We have y of s times s plus 1. Okay. And now I can divide all this term as follows. Y of s is equal to 3 times 1 over s minus 2 plus 4. And this is all divided by s plus 1. So we have y of s is equal to 3 times 1 over s minus 2 plus s plus 1 plus 4 divided by s plus 1. Okay? But here we have a problem, no? Here we can see that, well, we don't have any Laplace transform tables that looks very similar to this one. You can search in the tables and there is nothing like this. So what we need to do is to apply a partial fraction expansion. That is, you need to take this term, okay? And we need to expand it in the following way. A divided by s minus 2 plus b divided plus s plus 1. Okay, we need to expand this rational function to find these constants A and B. And now, based on these constant values, now we can apply the tables. Okay, but we need to expand this polynomial. Okay, but since here we don't have too much time to make this algebra class, what I recommend you to do when you are in this situation, what you can do is to use a function in your Texas that is called expand. Okay, and also you can use Wolfram to expand this rational function into its partial fraction expansion. Okay, so if you do that, okay, no, if you compute the partial fraction expansion of this part, you will obtain the following. No, you can, I will skip this, but you can use your Texas, no? If you want, in a minute, I can teach you how you can use your Texas in this situation. But the idea is that you need to expand this, okay? But because we don't have too much time to make all the algebra. And also this part is like the tedious part, no? Because we need to compute all these coefficients. And it can get really complicated, okay? So the idea is that you can input this rational function into your Texas using this function, and you will observe that the partial fraction expansion leads to the following. We have 1 over s minus 2 minus 1 divided by s plus 1 plus 4 divided by s plus 1. So we have y of s is equal to mm, 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 just one moment. We have here we can simplify this as 3 divided by s plus 1 plus 1 divided plus s minus 2. And we can now, with this simplification, we can now compute the inverse Laplace transform. Okay, that is y of t is equal to the inverse Laplace transform of y of s. That is equal to the inverse Laplace transform of this term. Okay, plus the inverse Laplace transform of 1 divided by s minus 2. Okay, this is the way in which you can do it. And you can see, or if you analyze this very closely, this is essentially the Laplace transform of an exponential. So we can compute the inverse Laplace transform, okay, as 3 times minus t for this one, plus e elevated to the minus 2 times t for this one. Okay, and this is the result. Okay, so the only step that you can miss is this partial fraction expansion, no? When you are basically solving the differential equation for y of s. Okay, but for the rest of the process, well, you can use the table. So the trick is that you need to identify the table that looks very similar to your function. Either you are in the time or you are in the S domain. And based on that, you can solve the differential equation, okay? The only thing that I will recommend that you do is that you need to, you can use this function in your Texas to expand this rational function, okay? And the reason for that is that, well, I don't want to waste too much time in this part because I wanted to tell you how you can use this Laplace transform by, yeah, we can solve the differential equations, but also we can generate a model that we can simulate very easily in MATLAB in order to study the dynamics of the system, okay? So just take that into account. And I will make another example just for you to, to be clear. And okay. So we have here another example. No, let's make, now I will make a second order differential equation. Okay. No, only to tell you how you can do that. So just one moment. Well, we have the following second order differential equation. We have this the y double prime plus y prime is equal to 5 times the cosine of 2 times t. And the initial conditions, we have that at times t equals 0, the initial condition of y is equal to 0. And also, well, since here we have a second order differential equation, we need to also have an initial condition for the first order derivative, that in this case is also 0. Okay? So again, remember, the first step is to apply the Laplace transform to all the differential equation. So we have the Laplace transform of y double prime plus the Laplace transform of y prime is equal to 5 times the Laplace transform of the cosine of 2 times t. Okay? This is the this is the definition. And now what we can do is to apply the Laplace transform to each term. So here we have a second order differential equation. So we know that the Laplace transform of this second order differential equation is s squared times y of s minus s times y of s, okay, minus um, minus, well, sorry, this minus s is this is not a y of s, this is the initial condition of the function minus the initial condition of the first order derivative, okay? Plus the Laplace transform of a first order derivative, that is s times y of s minus the initial condition of the function, that is y of 0, okay? And this is equal to 5 times the Laplace transform of the cosine. But we note that the Laplace transform of the cosine should be equal to s divided by s squared plus omega squared. But here omega squared is 4. And well, we can substitute the initial conditions, but the two are 0, so we can eliminate this part and this part and this part. So we can simplify the left side as s squared times y of s plus s times y of s. And this is equal to 5 times s divided by s squared plus 4. So what else we can do? Well, we can solve the equation for y of s, that is s squared plus s. And this is equal to 5 times s divided by s squared plus 4. Yeah, and if we solve for y of s, we can obtain the following. We have 5 times s divided by s squared plus 4. And you need to divide all this by s squared plus s. Okay, so this is the way in which you can solve it. I will express this in a different format. Mhm. So we have y of s is equal to 5 times s divided by s squared plus 4 times s squared plus s. Okay, and this is the step in which you need to expand this function using the partial fraction expansion. Okay, but you can use your calculator in this step. Okay, and if you introduce this rational function in your Texas, you will obtain the following. You will obtain that y of s is equal to minus 5, okay, divided by s squared plus 4 plus 1 divided by s squared plus 4 is, no, sorry, this is not minus 5, this is s. okay? Plus 1 over s plus 1, okay? So, well, this is the result. We can apply now the inverse Laplace transform to this function that is the inverse Laplace transform of y of s is equal to minus the inverse Laplace transform of s divided by s squared plus 4 plus the inverse Laplace transform of 1 over s squared plus 4 plus the inverse Laplace transform of 1 over s plus 1. Okay? So here it's quite simple. In fact, if you analyze this, you can see that this is the Laplace transform of a cosine. So we can compute directly, no? I will skip this step, but if you look at your tables, you will see that this is the Laplace transform of a cosine. So the inverse of that, of this function is minus the cosine of omega. But here omega is equal to 2, okay? Plus, we have here, well, here we have a problem in this side because here we need to multiply the numerator and the denominator by 2. And the reason for that is that, well, this looks very similar to the Laplace transform of a sine wave. The problem is that we don't have the omega in the numerator. So we can multiply the numerator and the denominator by 2. Okay, I will erase this part only to be clear about this step. So we have here 2 and 2. And if I introduce these two inside this transformation, now we can apply directly the inverse Laplace transform of this term, that is 1 over 2 times the sine of omega, but in this case, omega is 2 times t, plus e elevated to the minus t. Okay? Because this term is equal to the Laplace transform of an exponential, so we can say that the inverse Laplace transform is essentially an exponential function. Okay? And this is the result. Okay, this is like the way in which you can compute all of these transformations. Okay, so we have seen today how you, so I know that's a lot of information, but I only wanted to introduce you what is the overall methodology. Okay, and also you can use your Texans to compute the partial fraction expansion. I don't have a problem with that. You can skip that step because if we don't use that, we will lose a lot of time trying to compute that. And also, there could be errors, no? Because more than be a difficult problem, it's like a tedious problem that we need to solve. But you can use the calculator for that particular step. Okay? So that's all for me for this first video. I hope you like it and see you later.